In this video, I want to talk about products of affine varieties, which is a topic which is not covered in so much detail in the notes of Gutmann. So here we're going to explain some of the more basic things and results that go into this topic. So the basic setup is that we have already seen in an exercise in one of the first parts of this chapter that if you have x inside am and y inside am, two affine varieties, then you can always take x cross y in an cross am, which is just the same thing as an plus m. And this subset turns out to again be an affine variety, with the idea of the exercise that we're also going to see later being that if you have a set of equations cutting out x and a set of equations cutting out y, and if you just write down the union of these two sets of equations, taking kind of the first n coordinates for the equations in x and the last m coordinates for the equation in y, then this new system of equations cuts out exactly this product. And today we want to make this a bit more precise, not just write down some set of equations which cuts out the product, but actually show that essentially the equations which I described are all the equations on this ambient space vanishing here. So to make this precise, let's say that Ix inside the coordinates ring in n variables is the ideal of x, and Iy in these m variables is the ideal of y. And then, well, the ambient space, this an plus m, this has coordinate ring R, which is just the coordinate ring in these n plus m variables, which is the same thing as the ring of polynomial functions on this variety, an plus m. And then inside there, we define an ideal which we hope will cut out x cross y, which is, well, you take all the functions vanishing on x. So these will be functions just in these first variables, and then you're allowed to multiply them by arbitrary functions in R, and similarly for y, and you take the sum of these ideals, and then clearly you get an ideal inside this ring R. And then the big proposition here is that in the setting that we put up above, we have that the ideal of x cross y is just this ix cross y here. So these are all the functions vanishing on x cross y. And moreover, the ring of polynomial functions, or the coordinate ring of this product x cross y, is just given by, you take coordinate ring of x, and then you take the tensor product over k with the coordinate ring of y. We're going to recall this here in a second, but I mean, this here tells you, if you want to remember just one slogan from this video now, is that the coordinate ring of a product is the tensor product of the coordinate rings. And that's a really interesting and useful identification of the tensor product. I mean, in general, the tensor product is a very important construction in commutative algebra, and this here gives you one interpretation. Okay, and so let's recall, just to get everyone on the same page, let's recall some general facts on tensor products. So to set it up, let's say that A and B are any rings together with ring morphisms from some common ring C, maps to both of them. And then we can form the tensor product A tensor over C with B. And so a priori, what we do here is we use this ring morphism to see A and B as modules over C. And then we can define the module A tensor over C with B. And my claim here is that this is not just a C module, but it is in fact also a ring, and that's also a C algebra, with the product just given by, on these pure tensors, like this, just given by, well, take the product in the first slot and take the product in the second slot and then tensor them again. And this can be extended bilinearly onto all tensors inside this tensor product. And as an example, so if you haven't seen this before, this is kind of a useful thing to check, that this coordinate ring R that we had above in these n plus m variables is just the tensor product of the coordinate ring in n variables and the coordinate ring in m variables. And I mean, if you think about it for a second, this is easy to show just kind of writing down what are generators here and here. But this is also a special case which says that the coordinate ring of a n plus m is the coordinate ring of a n tensor the coordinate ring of a m. And this is the basic ingredient which we're going to later use. And then kind of a purely commutative algebra lemma, which tells us like how does this ideal that we saw before, this kind of ideal, how does this relate to anything, and how do you compute the quotient of the ambient ring by this ideal? So here the setup is inside A, let's find some or let us be given some ideal IA. Inside B, we have some ideal IB, and then we define I of A comma B as well, exactly this construction above. You take the ideal in A and multiply by arbitrary elements of the tensor product and the ideal in B. And you can, well, if you, maybe you're already happy with this notation here, but you can also define it just as the ideal inside this ring here, generated by two kinds of elements, namely IA tensor B, where IA is in the ideal IA, and B is an arbitrary element of B, and union with, well, A tensor IB, kind of the opposite way around. A is an arbitrary element of A, and IB is in the ideal here. So just by definition, it's an ideal generated by some stuff in here. And so we're allowed to take the quotient. This will again be a ring. And what the lemma does is it identifies this quotient here as, well, saying if you want to take this modulo this constructed ideal, it's the same thing as taking A modulo the ideal IA tensor B modulo the ideal IB. And the concrete map that you look at is it takes a equivalence class of A and the equivalence class of B and sends it to the equivalence class of A tensor B. And again, you extend bilinearly to get this result, which uses the defining property or universal property of this tensor product. The claim is this map is an isomorphism, so you can compute such quotients here just as the tensor product of the respective quotients. And I mean, I'm not going to give the full proof, but the idea of the proof is that first of all, you convince yourself that this map here is well defined, because I mean, you defined it on some tensor products of equivalence classes, so you should make sure that this element here is independent of these choices. And then what you can do is you can write down an inverse to this morphism, again, check that it's well defined, and check that the two compositions give the identity. Okay. So this was just some general results on tensor products. And now we go to the proof of this proposition. So recall, we want to show the ideal of I cross Y is this ideal defined here above, and the coordinate ring of X cross Y is the tensor product of the coordinate rings. And so inside this ring here, we want to show I of X cross Y is the sum of the ideals. And one thing that is really not so hard to show, and this is what is needed for this exercise, which we had at the beginning of the chapter, is that if you take this thing here, basically I of X plus I of Y, and take its vanishing locus in A n plus M, then you exactly get x cross y. And the idea here is that if you have an element a comma b in this big ambient space, then if you require that all the functions in ix vanish on this point, this forces a to be in x. And if you require that all functions in I or y vanish on the point, this forces the second component b to be in y. So this is not so hard to show. And so using the Nullstellensatz, we can then apply ideal on both sides. And then we get the ideal of x cross y is the ideal of the vanishing locus of this ix cross y. So this gives exactly the radical of this idea here. So we wanted to show this is this ideal. We have shown this is the radical of this ideal. So it suffices to show that this is the radical ideal, that taking the radical doesn't change anything. And then in general, it's true that some ideal in a ring is radical ideal if and only if when you take the quotient ring, then this is a reduced ring, which means 0 is the only nilpotent element. That's just basic commutative algebra. And so this allows us to reformulate this problem here as a problem about this ring, which, as you're going to see, we want to compute this ring anyway, so it's also a bit economical. And then, well, computing this ring, we just plug in the definitions. And then one thing we saw as this example was that this ring R here is just the tensor product of these two coordinate rings. And then we take this tensor product and we mod out by this particular ideal. And this was exactly the setting of the lemma, which told you that taking such a quotient, you can also take the quotient of the first ring by the first ideal and tensor with the quotient of the second ring by the second ideal. That was where we needed the lemma. And then if you just look at this, this is polynomial ring modulo ix. This is just by definition or by the property that we saw above, this is just the coordinate ring of x, and this is just the coordinate ring of y. And that's not so surprising because in the end, this is what we want to show is the coordinate ring of x cross y. And so returning for now to where we were in the proof before, we wanted to show this is reduced. And we have identified it now with this particular tensor product of coordinate rings. And now we use a fact, and this fact is actually not super easy. I mean, you need to input some thought in this, but it's again a commutative algebra fact which says if K is a perfect field, and if T and U are reduced K algebras, then the tensor product is reduced. And that's the kind of nice result we want, because now we want to show some tensor product of some algebras is reduced. And if we assume this fact for now, then we see since I of x and I of y are radical ideals, that was another consequence of the Nullstellensatz. We have that their quotients, the quotients of these rings here, are reduced. This uses the same equivalence that we had here. And so we did get a tensor product of reduced K algebras over K, or base field. And since we have the ongoing assumption that K is algebraically closed, in particular, it is also perfect. And so we are allowed to use this fact. And then it tells us that this is indeed a reduced algebra. And then we have fulfilled all of our debts. We've shown this is radical, and so indeed we have proven the first part, that the ideal of x cross y is this particular sum of ideals. And then finally, we did already now compute this ring here, because this ring by definition is just the ambient coordinate ring modulo the ideal. And well, this was exactly this calculation here, which told us that this is the tensor product of these ideals. And in particular, this map from this tensor product here is well defined and an isomorphism. Okay, so that was the end of the proof. Let me just say a couple of words here. So this fact, this I won't give the argument here, but in the description of the video, I'm going to give you a link to a place where this is proven. And this needs really some techniques, but I think in principle you have learned everything in the last lecture on commutative algebra to see this. Note, it's tempting to, I mean, if you just stare at this, you might believe that, well, if T and U are reduced, then also the tensor product is reduced without any assumptions on the field. But this turns out to not be correct. So this is one of these kind of false friends. And there are explicit counterexamples for non-perfect fields where this just goes wrong. And I think these will also be mentioned in the source which I give. So here you actually have to use something about the field over which you take the tensor product. Okay, that's everything about products of affine varieties for now.